So today, we're going to talk about something called continuity. Really simple idea and something that you've probably known about for years. A graph or a function is continuous. Well, it's so easy if you look at it. My favorite definition is one that you could tell an elementary school student. If you can draw a graph without taking your pencil off the paper, it's continuous. However, also I could use the same thing for a function. You can draw a function without taking the point of your pencil off the paper, which is wonderful until you have to draw like the little arrows on the ends, and you have to take your pencil off the paper to draw the arrow. I guess you could find a way of drawing it. But then you also have the people who are saying, well, what about this? And then they draw a hole in the middle of your graph, and now it's not continuous. There's a hole in it. So there's loopholes in this. We're going to go through the specific definition for continuity in calculus. But first, let's just take a look at some of the obvious bits about continuity. Hey, look, we realize that continuity actually represents, something that doesn't have any holes, any breaks, any asymptotes, or anything like that. So we realize that continuous means it just keeps going, but there are different types. For instance, this square root function here, it's continuous everywhere on its graph, except it's got a specific domain. It actually starts at 0, and it includes the point 0. So, the domain of the function actually tells you where it is continuous. Likewise, a logarithm function, that's base b, that's not 6, but it could be any number there. A logarithm is the same thing. It's a continuous function, but it has a limited domain. So we say that it is continuous only on that domain of 0 to infinity. This time we don't even include the 0. Hey, look, we even have a bunch of special trig values like tangents, cotangents, secants, and cosecants, where there's vertical asymptotes that naturally break up the graph. Now it's much more difficult to state the domain, and much more difficult to state where it's continuous. But basically where the function exists, it is continuous. There's no breaks except for the asymptotes. So you just leave those out of there at every odd multiple of pi. The 3 dots indicate you continue on in that same pattern. You may not have studied the greatest integer function before, but it is a step function. It literally is all the steps. And what it means is round down. We'll talk about this more in class. But notice, it is a piecewise function. It's made up of all these pieces, and so the domain is actually everything from 0, including 0, to 1 for that first step. And then it goes from 1 to 2, including the 1, but not including the 2. The domain is actually going to be right here, where the domain is any integer to the next integer. You include the left-hand point and you don't include the right. So what's the continuity of this? Well, it's continuous exactly where the domain is. The domain tells you. So if you want to find the continuity of a function, just determine its domain. You've been doing that for years. Now here's an example of a piecewise function. You might remember these. This is where you put 2, 3, 4, even 20 different functions all together, but they all have certain domains. And here's where continuity could get a little tricky. Is something continuous at 3 separate areas? Is that really where it's continuous, or could it be continuous elsewhere? If you take a look at the first function, the blah function, d blah, if you look at blah and de, those are made up, by the way, just so you know. Do they actually look continuous here, or is there a break or a jump discontinuity? Well, it turns out they're not continuous. So the continuity would be from negative infinity to negative 3, not including it. But then you look at the next 2 functions and you realize where one function ends, the other one picks up and begins. It doesn't look very smooth, but perfectly honestly, this is continuous. One function flows directly into the next. So the continuity for this piecewise function, well, the continuity is right here. It turns out that it is continuous, not on 3 different parts, but really on 2, because 2 of these combine. So when we're looking at piecewise functions, you have to check and see, do the endpoints match up? I'll show you how to do that very shortly.